Hi everyone, greetings from sunny Florida. I tried to get these videos done before I left, but technology wasn't working with me. So here I am in Florida. While my friends are on the beach, I'm going to talk to you about polynomial functions. So first things first, let me give you a little glimpse of the view out of my room. It's a little bit dark, but there's a palm tree. Awesome. Okay, but now back to polynomial functions. Okay, so on this program, for whatever reason, I don't understand it. I cannot do a video that's more than 10 minutes long. So you're going to actually have a couple of different videos going on. So you'll do this one, and then there should be another link below to hopefully finish it all out. So it should just be 2 videos, and yeah, we'll see how it goes. Okay. All right, and the nice thing about these videos is that if you have a need to stop the video so that you can write something down or finish up, that's great. You can pause it anytime you want, so I don't have to spend time waiting for you guys to write stuff down. Okay, so here we go. We're going to start out with the definition of a polynomial function. This is our next unit, and here it is. This is the technical definition. Let n be a non-negative integer. So we'll talk about what that means in a minute. And then we have all of these letters, a sub n minus 1, and so forth. Let those be real numbers. Then we have this function written with all the letters. It's called a polynomial function of degree n, and a sub n is the leading coefficient. Okay, what does that mean in other words, or in maybe we might even say in English? Well, when we're talking about polynomial functions, we want one where the exponents on x are greater than or equal to 0, that's the non-negative part, and they are integers, meaning there is no decimals or fractions, and the coefficients are all real numbers, meaning they're not I. So here's some examples of, whoops, I think it's freezing. See? Sorry, examples of some equations. We have the first one here, f of x is negative 3x to the 5th plus the square root of 2, x squared plus 5. This one is a polynomial function. You'll notice that all of the exponents on x are positive, 5 and 2, and they are not decimals or fractions, so that's good. And all of the coefficients are real numbers. Negative 3 is a real number. The square root of 2 is a real number, and 5 obviously is a real number. Right, next we move on to g of x. Why is g of x not a polynomial function? Well, g of x is not polynomial because you'll notice the very first term we have, this negative 3 over x squared. X squared, because it's in the denominator, would actually be rewritten as x to the negative second power, which would make it have an exponent that is negative. Remember, the exponents have to be positive. So that is not a polynomial. This next one, this large or capital F of x, is not a polynomial. Why? Because we have x, the square root of x, which would be x to the 1/2 power. Not okay. That's a decimal or a fraction, so that's not okay. But this capital G of x is a polynomial function, and it has a degree of 6 because we have x to the 4th. But if I were to multiply all of this out, the largest power of x would be 6, because x times x would give us an x squared, times this x to the 4th would make it x to the 6th. That's why that has a degree of 6. Okay. Some other important information about polynomial functions. Their graphs are what we call smooth and continuous. So I have several examples here. We have this graph, which is smooth and continuous, so no sharp points on it, and also there are no breaks in it. The second one here is also smooth and continuous. That is a polynomial function. However, the two at the bottom are not polynomial. Can you tell why? This one has a break, so that's not continuous. This one has a sharp corner or edge or point on it, and so that is would make that not a polynomial function. Okay, polynomial function graphs are smooth and continuous. So in a couple of days we'll be graphing polynomial functions, and you need to be careful to make sure that you're always drawing them with smooth curves. Okay. we can determine a lot of information about the graph of polynomials from their equations. The first thing we're going to talk about is the end behavior, or this means what's happening on the far left and what's happening on the far right-hand side of the graph. That's the end behavior. And this becomes really important when we get to calculus. Actually, thinking about end behavior has a lot to do with limits, but we'll talk about that later. So, there are 4 different possibilities. We have the degree is odd, and the leading coefficient, which I'll abbreviate as LC in the future, is positive. Then the graph is going to fall left and rise right. So here's a couple of examples of that. And one of those is just a polynomial function, just a random one. This one, though, obviously is a line. And so if you think about the degree of the equation of a line is 1, that's odd. If it has a positive leading coefficient, that's a positive slope. So this, you can tell this has a positive slope. Next, if the degree is odd and the leading coefficient is negative, then the graph rises left and falls right. So it's just the opposite of that. So one of the ways to remember this, that odd degreed functions do opposite things on their ends. Okay. When we get to the next page, with positive leading or even degreed polynomials. Hello, it's been a long day. The even degreed polynomials have, you'll notice, the same behavior on the ends. So in this case, with a positive leading coefficient, rises left and right. And you'll notice that I use a quadratic to help us see that, because that's going to obviously have a degree of 2, which means and it opens up because it has a positive leading coefficient, so that rises left and right. And obviously then the degree is even, the leading coefficient is negative. It's going to fall left and right. So those are going to be like a parabola opening down. Okay. Next, we're getting pretty close to the end of this one. Zeros of polynomial functions. What are zeros? So the term zeros is pretty much synonymous with things like x-intercepts, roots, solutions, all that good stuff. To find the zeros, we let f of x equal 0. Okay, or you think about, how do we find x-intercepts when we're looking at something? We always let y equal 0 and solve for x. So it's the same thing. We'll solve those equations by factoring. And you'll notice I said on there, more on this later, we're going to talk about how we can factor some of the higher degreed polynomials past quadratics, past cubics. So we'll talk about that when I get back. Okay. All right, so here's an example, the first example. So find all the zeros. So you'll notice we have a cubic equation. What I did from, let's see, what did I do here? Oh, first step to second, we had the function. Then we have to let f of x equal 0. Then we started factoring. So I used the grouping method. So I grouped the first 2 terms together, the second 2 terms together, and applied grouping to those. You'll notice that once I did group, I ended up with x minus 1. And x squared minus 1 is factorable, so I also went ahead and factored that according to the difference of 2 squares. Then I set each factor equal to 0, and we find out that our zeros for this function are -3, -1, and 1. I'm going to need to stop the video here on this one, and I will be back short, or you can click on the next video so that you can see the rest of the lesson. See you in a minute.